So welcome back to our third lesson in Unit 1. This lesson is on parent graphs of functions, and we're going to use this foldable graphic organizer to take notes in this section. So if you want to follow along with these notes, you can either print this foldable or you can make your own by folding just a regular sheet of printer paper with the sides in toward the center, and then you'll cut some tabs on the front side, sort of like a window shutter, and label them constant, linear, quadratic, cubic, absolute value, square root, cube root, rational, ceiling, and floor. Okay, all of these you should have seen before in Algebra 2 at some point, with the exception probably of ceiling and floor functions. This is not, however, an exhaustive list. As the year progresses, we're going to add to this family of functions parent graphs for exponential, logarithmic, logistic, and some trigonometric functions. So we're just going to start with these 10 before we look at transformations of functions in Lesson 4. And we'll organize our notes and ideas about these graphs in this foldable. Okay, so the first thing I want to look at is what is a parent graph. And a parent graph is the most basic graph of a function in algebra. It's one in which no transformations have yet occurred. And if we take a look here in Desmos, here we go, at this graph of a parabola, that's just the most basic quadratic function, f of x equals x squared. A transformation would look like taking a new function g of x, and we're going to make that be the original function f of x, but we're going to add 2 units to that graph. So if you notice now, this parabola, the parent graph, just regular old x squared, it's been transformed, it's been relocated, its vertex is now moved up 2 units. Right? I could change the graph by dilating it, so maybe I'll multiply it by 1/2. So 1/2 times that parent graph f of x. And now you can see that the darkest curve here, 1/2 f of x, is wider than the parent graph of x squared. So those are called transformations. Transformations we're going to look at more closely in our next unit. But in order to have something to transform, we have to have something to start with, and that's called the parent graph. So x squared is the simplest form, right, of any of these, but they all have that basic parabola shape that makes it part of the family of quadratic functions. Okay, so that's what we mean when we say parent graph. Okay, the next slide here is going to organize for us on the front of this foldable our parent graphs that we're going to examine and put them into categories of functions that go together. So the first 4, constant, linear, quadratic, and cubic, these are called polynomial functions, right? And if you remember from algebra when we studied polynomials, we identify them and classify them based on their degree. The degree of the polynomial is the highest exponent in that polynomial. So a constant would be a polynomial of degree 0. Linear is degree 1. Quadratic is degree 2 because it's the x squared, right? Cubic is x cubed, so that would be a degree 3 polynomial, and so on. Okay, absolute value is not a polynomial function. Okay, it's its own special function that takes the value of x and tells you its positive distance from 0 on the number line. So if you put in a 3, right, the positive distance between 0 and 3 is 3. If you put in a negative 3, the positive distance between negative 3 and 0 is still positive 3. So some people like to think of the absolute value as a function that makes or keeps everything positive. Okay, then we have the square root and the cube root. These are the radical functions. The rational function, that happens if you notice the word ratio here in rational. That's whenever you have an equation that's a fraction that has an x or a variable in the denominator of that fraction. That's called a rational function. And then these two new ones you may not have seen before. They're called our step functions, the ceiling and the floor. You might also know them by the name greatest integer function instead of ceiling, or least integer function is another way that will refer to the floor function. Okay, so that kind of gives you a sense of how these parent graphs are going to fit together in the function families. Okay, the first one that we want to look at is the constant function, and its equation is f of x equals k, where k is any real number. And that graphs a line that's horizontal on the coordinate plane. And if we look back again at, okay, so if we want to look at the graph of a constant function in Desmos, I can create a slider by typing in a variable k, and then clicking on add slider. And so now when k is 1, you can see here there's a horizontal line across the coordinate plane where y equals 1. If I make that a higher value, right, you can see up here now at 7, when k equals 7, the horizontal line is up there. When we go down to negative values, right, k could be -5, now the horizontal line is down at y equals -5. And so on. We could have a k equal to 0, and then the horizontal line is right along the x-axis. So we have lots of options there. Any real number really could be the value of k, and it's going to always make that horizontal line through the graph. So the anchor points then for the constant function are, whoops, that should say 0, k for the y-intercept. Right, then we have -1, k, +1, k. It doesn't matter what value we put in for x, the output, the y value, is going to always be k. The domain then is all real numbers, -∞ to +∞, and the range is just the single element k. So we use set notation to write the range. Okay. The next graph that we want to consider in our parent graph family is the linear function. The linear function's equation is f of x equals x, or y equals x, which is why it's also called the identity function. In a lot of textbooks, including the textbook we use, they call it the identity function, because whatever goes in for x comes out for y. So if we put in 0, we get out 0. If we put in 1, we get out 1. 2 brings out 2, right? -1, -1. So our anchor points for the parent graph are the origin, 1, 1, and -1, -1. The linear function, remember, is part of the polynomial family. It's a degree 1 polynomial, and its domain and range are both unbounded. And it's going to be always graphing a diagonal line. Okay. The next function that we want to look at is the quadratic. And the quadratic function is f of x equals x squared. That's one that we started with in this lesson when we were looking at Desmos with some basic transformations. Since it's x squared, it's also known as the squaring function in our textbook. And it's going to always graph a parabola. Okay, so parabolas are U-shaped graphs. The parent function passes through the origin, 1, 1, and -1, +1. Later on in Unit 2, we're going to learn that that symmetry about the y-axis indicates something called an even function. So the quadratic parent graph is even, and its domain is fully unbounded, -∞ to +∞, but the range is a half-bounded interval. It includes the 0 and then heads up to +∞. So in interval notation, we put a bracket on the 0 to indicate that that is inclusive. And then that brings us to the cubic function parent graph. Since the equation is x cubed, it's referred to as the cubing function in our textbook. It graphs a vertical wiggle. right? I wish that there was a more mathy word, like the quadratic function graphs a parabola, which is a really fantastic math word. There is no special word for the cubic shape, so we just refer to it as a wiggle or a squiggle. But this wiggle is headed up and down as opposed to left and right, which we'll see one that's like that in a few moments. It is a polynomial of degree 3, and it's passing through the anchor point 0, 0, 1, 1, and negative 1, negative 1. So these anchor points for the cubic function are the same 3 anchor points for the linear function. It's just the shape of the curve that goes through them is different. Okay, its domain and range, though, are identical to the linear function, all real numbers for both the domain and the range. Okay, so that brings us out of the polynomial parent graphs, and we're going to take a look at the absolute value function's parent graph. If you recall, the absolute value of a number, you put in the number, you get out the positive distance to 0 on the number line. And because all of the outputs have to be positive, there is nothing in the negative y-axis here. So our range is half-bounded interval from 0 to infinity, including that 0. So it's got the same range, same domain as the quadratic function, but instead of graphing a U-shaped parabola like the x squared function, the absolute value graphs a V. So it's got this real sharp pointy vertex there at the origin. Okay, then our next set of parent graphs that we want to consider are the radical functions. There are 2 radical functions that we're going to look at today, the square root function and the cube root function. Okay, the square root function is a radical with an index of 2. So like inside the hook of this square root, there's an invisible 2. We got lazy over the years and quit writing it, but it's still there. So the index is 2, and it's the inverse of a quadratic function. So if you remember, the quadratic function graphed a parabola like this. The inverse of that parabola would look like this. But because that fails the vertical line test, that sideways parabola that is the inverse, I can't keep the whole thing because I need it to be a function, a square root function. And so that's why we only keep the top half of the parabola here. Oops, my eraser. There we go. So top half of the parabola, right? When I get rid of that bottom half, now what I've got left is going to pass the vertical line test and stay a function. So the square root of x is the undoing or the inverse of the quadratic. It graphs a half of a sideways parabola, which we can see right here. Its anchor points are 0, 0, and 1, 1. However, it's special in our family of parent graphs because its end point is at 0, 0. None of the other parent graphs have an end point, right? This is the only one that has that special feature. So its domain is a half-bounded interval as well as the range. So both domain and range start at 0, including the 0, and head off to positive infinity. Okay. Our other radical function that we're going to look at today is the cube root function. It has an index of 3. Right? You can see the little 3 there in the hook. It is the inverse of a cubic function, and its anchor points are so interesting. So the anchor points of the cube root function are exactly the same 3 anchor points as the linear function and as the cubic function, right? So 1, 1, 0, 0, negative 1, negative 1. But its shape is unique, right? It's a wiggle like the cubic was a wiggle, but instead of being a vertical wiggle like the cubic, it's a sideways wiggle. So it wiggles from left to right here through those same anchor points as the linear and the cubic function. Its domain and range are fully unbounded, so all real numbers for both domain and range. And then that brings us to the rational function. Our textbook refers to the rational function as the reciprocal function because the reciprocal of x is 1 over x. same way like the reciprocal of 2 is 1 over 2. So that's why it's referred to as the reciprocal function. We call it a rational function because if you see the word ratio here in the name rational, and the function is a ratio where the x is in the denominator of the function, so hence the name rational. Rational functions graph a shape called a hyperbola, and that's a curve that has 2 sections to it. So this is one graph. It is the graph of the function 1 over x, and it produces 2 curves that are separated by these invisible barriers called asymptotes. And generally we sketch asymptotes using dashed lines. So this graph has a vertical asymptote here at 0, and then a horizontal asymptote here where y is 0. So x equals 0, y equals 0, those vertical and horizontal lines are like dashed, dotted fences, if you will, that keep the curve locked in those quadrants where you see it. So the reason why we have those asymptotes there is because it's impossible to divide a number by 0, right? So if x equals 0, I would have 1 over 0, which is undefined. So there can't be a point on this graph where we can put in a 0 or that we could output a 0, right? So 0 is restricted from both the domain and the range. And we can show that in interval notation by a union here of the interval of all the negative numbers, so negative infinity to 0 non-inclusive. We hook that up with all the positive numbers from 0 to positive infinity non-inclusive, and that gives us the set of all real numbers excluding the 0. Right? And don't forget when you're doing interval notation to join up your multiple intervals with a union symbol. And then, so we're going to slow down for just a second, and before we dive right into the features and characteristics of those parent graphs, let's just look at what the ceiling function and the floor functions actually do to the value that you put in to that notation. So when you see a symbol like this, where it's sort of like straight up and down the way an absolute value is, but there's these little lines or bars on the top of it, sort of like it's got a ceiling coming over it, right? That's called the ceiling function, or the greatest integer function. And what that does is it rounds non-integers up to the next integer. Okay, what we mean by non-integers are decimal values or fractions like these first two. If you put an integer into the ceiling or the floor function, it just returns the same value. So the ceiling of 2, since 2 is an integer, it just returns 2. Okay, but for these decimal values here, it's going to round these up to the next highest integer. It doesn't have to be like 0.5 or higher to round up. It's going to round anything up that isn't already an integer. So 0.2, that rounds up to 1, because 1 is the next highest integer. Okay, 3.4 also is going to round up to its next highest integer, which in this case is 4. So when you look at the graph of the ceiling function here, you can see, for example, the 0.2 would be right here on the x-axis. Its output is up here at positive 1 on the y-axis, right? 0.5 would output a 1, 0.99999 would output a 1, and so would 1, right? So the ceiling of 1 is 1, and so that's a closed circle. We have an open circle on the graph of the ceiling function at the point 1, 2, because when I put in 1, I get out 1, right, not 2. But if I put in 1.0001, that's just ever so slightly past the integer value 1, and that is an output of 2. So that's why we have to indicate on the graph where the open and closed circles are on that ceiling function so that people don't get confused about what is and is not inclusive. Okay, over with the floor function is going to work the same way, except we round non-integers down to the next integer. So 0.2, its floor rounds down to 0. right? 3.4, its floor is going to be 3. 2, because it is already an integer, it's going to stay the same output. So the floor of 2 is 2. So when I look at this graph of my floor function, you'll notice that as compared to the ceiling, the open and closed circles on the ends of these steps are reversed. And if I look at, let's see, 2, so the floor of 2 is 2, right? The point 2, 2 is inclusive on both graphs, right? Here's 2, 2, it's a closed circle on the ceiling graph. Here's 2, 2, it's a closed circle on the floor graph. But the reason that these get reversed in like this one is open then closed, this one is closed then open, is because of where it starts. So since this floor function, it starts with 0 inclusive, and then the floor of point 1 is still 0, point 2 is still 0, point 3 is still 0, all the way up to point 999, right? Because it creates this line segment between 0 and 1 non-inclusive along the x-axis, that's why it's starting closed and ending open. When you look at the ceiling function, right, if you imagine like a little person standing here along the x-axis, right, there's my little guy. See how the first bar there is a ceiling over his head, like a roof over his head, versus the person who's standing here along this section of the positive x-axis, he's standing on a floor. So that's just a way, like a quick way you can recognize which graph is which if you forget, you know, the direction of those closed and open circles as a strategy to remember. Okay, so if we look at the graphs then in our graphic organizer, the ceiling function is f of x equals the ceiling of x, and so the notation has these little bars on the top where the ceiling is. It's also known as the greatest integer function. It's a step function, right, because its graph looks like little stair steps going up, and it rounds non-integers up to the next integer. Its anchor points are 0, 0, 1, 1, negative 1, negative 1, which is so interesting, right? Again, it's the same anchor points as linear, as cubic, as cube root, just a very different set of a picture that goes through those anchor points. The domain is unbounded, negative infinity to positive infinity. The range, however, is just the set of integers. And if you remember, we talked about in the last videos that this symbol, 2 slashes with an R, right, that symbol means all real numbers. Okay, and if you wanted to use that set notation to represent integers, that looks like a capital Z with a double slash through the middle. That is the notation for integers. So if you don't want to write out the word integers, you're more than welcome to just use that Z with a double slash to indicate that you're talking about the set of all integers. So that would be the ceiling function. The floor function is the last one that you want to put into your notes, and that is the lowest integer function. It's a step function rounding non-integers down to the next lowest integer. Your domain is the set of all real numbers. The range is the set of integers only. And then you can go ahead and attach that graph into your notes for the floor function. Okay, we're going to stop there for the parent graphs and give you a chance to practice using them and recognizing them. And then in our next lesson in 1.4, we're going to start doing transformations with these parent graphs.